Okay, so right now we're going to talk about an object undergoing free fall. Just to make things simple, we're going to talk about an object that starts from rest and falls straight down. So the example we're going to use is a skydiver. Imagine they start off like in a helicopter or something that's just straight up, it's not moving left or right, it's just where it is. This person steps out of the plane. When they step out, they're going to start moving towards the ground, but they're not moving super quickly, which is why their first velocity is going to be really, really small. A force diagram that would go along with that would start off with that force of gravity on the skydiver by the Earth, pointing down towards the center of mass of the Earth. When they're in the air, the only other thing that would be touching them, besides the pull of the Earth, is going to be the air. But because this is the instant they left their plane, we're probably not going to have any amount of air resistance just yet. So this will be the only force that is currently acting on the skydiver, the instant they start their free fall. But a second later, they're going to be falling for a little bit. They'll have sped up. They're moving faster. The force diagram would, well, still consist of that same force of gravity. Their mass hasn't changed. Neither has that gravitational field strength of the Earth. So we have the same amount of force of gravity. But now, because they're moving through the air, we have some air hitting them. That'll be that force of drag. And because they're falling down, that air resistance is applied in the opposite direction that they're moving in. So we have a small amount of the force of drag on the skydiver by the air pointing up. But overall, the sum of the forces acting on the skydiver is still pointing down. So they're still going to be accelerating downwards, just maybe not as much as that initial instant. Second after that, they're moving even faster still. They have the same amount of force of gravity because once again, their mass has not changed, but they're moving faster through the air. So that's even more force of drag, more resistance. So it's more force of drag pointing up. But overall, we still have that sum of the forces pointing down. An instant later, they're moving even faster still. They still have that force of gravity, but now we can assume that they've been moving fast enough that they have a whole lot of force of drag acting on them. An equal amount as that force of gravity dragging them down. At this point, those two forces are the same size. This means that the forces will now be balanced on the skydiver. At a certain point, the skydiver cannot speed up anymore. They're going to be going at the same velocity. That is their final velocity or the terminal velocity. So that way, an instant after that, they're going the same speed. And our force diagram is going to look exactly the same. An instant after that, same speed, same force diagram. The fact that the forces are balanced does not mean that the skydiver comes to a stop. What it means when the forces are balanced is that the acceleration is zero. The skydiver will no longer be speeding up. They're going to be continuing to move towards the ground. Because our force of drag is proportional to the size of the object and how quickly they are moving, that's one of the reasons why we know this force of drag should not be changing. We have no indication that the size of the skydiver is changing, and at a certain point, their velocity won't be increasing anymore, so they can't have any more force of drag. So unless there is something that happens to the skydiver, this is the same speed that they will be moving downwards with, well, until they either hit the ground or something ends up causing some change in the amount of force they have there, such as them pulling a parachute.